Hi everyone, this is Mohammed Sadek Asrampour, a PhD student at Monash University, Australia, and also CSRO. The title of this work is Energy-Aware Resources Scheduling for Serverless Edge Computing, that is co-authored by Adel Tusi, Rajgir, Mohammed Amir Chima. I would cover an introduction on the topic, system model and problem formulation. We then propose an energy-aware scheduler, and we evaluate the performance of that, and we finally conclude. Let's get started with this statement by Cisco. IoT devices will exceed 3 times global population by 2023, which means we cannot probably rely on the cloud computing for processing all the data produced by IoT devices. Instead, edge computing is the idea that is going to bring the computation closer to the edge to the IoT devices, where a controller node, or sometimes called a manager, orchestrator, or a gateway, is going to handle the management of a cluster of edge devices that are also called edge nodes. These edge nodes are going to do the processing, and all of them are connected to each other and to the IoT devices through communication means such as Wi-Fi, cellular cable, and so on. Something particular about the edge design in this work is that we are considering edge nodes doing both sensing and actuating. In other words, each node is producing the data and also is processing the data. And it means if a node is down or is failed, we are losing both. And we are also considering edge devices are powered by renewable energy sources such as solar irradiations and also are equipped with a battery. And a problem here is that in such a system design, we always know that all edge devices are not receiving the same amount of energy input because of the uneven distribution of energy. And also we know that all the nodes are not having the same amount of workload to execute. This is something that we need to consider. Otherwise, we can see that this node tree in here is called the bottleneck node, which is the one that is going to fail or go down before all of them, and it will leave the area uncovered. Here we have two concepts of operational availability, the time duration a node is up and running, and also quality of service in terms of response time, that these two are concerned here, right? Maybe the solution to address this will be proposing energy-aware resources scheduling solutions that can, for example, if an application is running on node 3 locally, you can just offload it to another node that has enough energy so this node 3 can survive longer. But the challenge here is that moving functions around and offloading them to another node is not very easy because the application needs to be very portable, so you can do such a thing, and you cannot achieve this using conventional deployment of applications. This is where we introduce serverless computing as a facilitator. Uh, Talking about serverless, let's just know about the serverful applications like what we already have. A serverful application is like running exactly on top of the OS, and it is tightly coupled with the host, and it's not always easy to move this around. Instead, serverless computing will give you function as a service, which in fact you have a template, you just need to put your code in it, and you are done with your task. Then serverless platform will containerize your code in terms of a function, which is bringing multi-tenancy and resource efficiency. Then it makes your function stateless by removing the state and storage, which is the best material for portability and moving around. And also serverless platforms are handling the load variability for you. It increases the number of replicas you need for a function and decreases it whenever it needs, but it actually doesn't know where to put the new instances, which is like another problem of resources scheduling and energy awareness. Looking more into serverless, we have some implementations of serverless in cloud platform like Amazon Lambda, Azure Functions, and Google Functions. We have open source platforms like OpenFaaS, OpenVis, Kubeless that normally rely on top of container orchestration tools such as Kubernetes, but they both have no idea what energy awareness is, which means the scheduling of functions in such a platform is usually based on random solutions or performance awareness or something like that. A sample use case that is considered for the edge design is this pest repellent system. For example, consider some fake owls equipped with a Raspberry Pi, some sensors and cameras are left all around the farm to repel the birds. If this nut tree is living by itself without an edge concept, it will just die and leave the area uncovered, and birds will just damage that area. But with making this server an edge computing environment and bring a serverless, we can help this farm, right? Based on this, we reached to this question that how to achieve energy-aware resource scheduling in serverless edge computing to improve operational availability, particularly for bottleneck nodes, while preserving quality of service on renewable energy and battery-powered devices. So we model a system for this and formulate the problem. The system model says, assume we have this binary variable for node availability that shows if a node is up or down. That is basically determined by the state of the charge on each node, if that's upper than a threshold. And this state of the charge is determined by the state of the charge before plus the renewable energy input, the consumed energy, and considering the battery capacity, right? We and we model it like the following, where the most important part is the consumed energy, that is a matter of consumed resources and communication cost. The consumed resources, that is the most important part, is also a matter of the functions running on a node and the number of replica of a function, because they are consuming the resources, specifically the CPU. The functions have a size, so we can determine how much CPU they consume, and the replicas are known based on the workload on the node. Based on these informations, we have a function placement mechanism that is going to decide for a node that how many local functions and how many offloaded functions a node needs to run. And an optimal solution will be trying to find the placement of such functions on. We model the problem as a bottleneck generalized assignment problem, where we try to maximize the operational availability of minimum available node, like the bottleneck node, subject to the point that all functions need to be placed. And if a node is down, no function scheduling for that will happen. And also we know that the capacity is a constraint. We have a demonstration to see what we mean. Assume on the left side we have three nodes, node D1 to node D3, and we have four time slots, T1 to D4. Without this optimization, node 3 will always be off. But with this optimization, we try to get some energy from other ones to give to this D3, so this one can survive, and we have some time slots that all of them are, or the majority of them are up and running. But this optimal solution is NP hard and also requires feature knowledge. Instead, we are going to propose our energy aware scheduler. The scheduler we have designed is based on the following this demonstration. Assume we have node D1 to D6. Each one has a function to be placed. The algorithm says sort nodes by their charge. Assume we have this state of the charge for each node from 0 to 100. And we also make some zones called well-powered zone, vulnerable zone, low power zone, and powerless zone with different range of state of the charge considered. And also we give a priority to the functions of each node based on their zone. Right. The algorithm says sort functions by zone priority. So we make a list of functions to be placed as you can see on the right side. Right, so the F1 is the first one to be placed based on the priority it has because it belongs to a well-powered node, well-powered zone that has the highest priority. Before placement, we also need to consider the capacity constraint. The algorithm says if a function belongs to a well-powered node, so place it locally. So F1 goes locally. Then it's turned to F5. For F1, we can consider offloading two other ones subject to three constraints. Capacity, if the node we are offloading this function to has enough capacity. Another one is reservation, which means the node we are offloading our function to needs to reserve some space for its own functions. First of all, then we offload always to a better zone, right? So F1 is placed now. F5 can be uploaded to D1, then F4, then we have F3 that can be uploaded to D3. But if you can see D2 and D3 are in the same zone, like vulnerable zone, so there is no point in uploading F3 to D2. Instead, it's placed locally. Then we place F2 on D2 because the resource is already reserved for that, and we ignore F6. But we have two novel constraints in this algorithm that are also going to work. One is warm scheduling. That means if a node is down, we can still offload its functions on another nodes. In case the node is coming up, the functions are always there and can start executing tasks without waiting for the scheduler in the next round to make a decision. We also have the concept of sticky offloading, which means stick with the node that you are offloaded to and don't move around. This is what the functions need to follow. Right, let's go for performance evaluation of this schedule. Where first of all, we have this setup where 5 Raspberry Pis are going to make a cluster and a controller is the master node. We uh, power the Raspberry Pis using Pi-Juice battery, and we measure the power consumption or energy consumption on them using the power meters. We give them renewable energy sources with different rates. We enable containerization. We deploy orchestrators such as K3s Kubernetes, the light version of Kubernetes, and we use OpenFaaS, the serverless platform. We have also a database release. And the main part here is the Pi agent, which is the code we have developed, a Python code of around 5,000 lines that includes the workload generator, the monitoring, and also the scheduler. So we have implemented different schedulers, including ourselves, to be run on this setup and be evaluated. And for this evaluation, we containerized a smart farming application that consists of three microservices: smart irrigation system, farming monitoring, and soil moisture monitoring. And we produce random workloads on each node with different rates. And the whole process is automated using Helm charts. And finally, we have this setup. The benchmark algorithms include the optimal solution that we just modeled, the proposed algorithm, which is the zone-based algorithm I just demonstrated, local algorithm, which is a scheduler that always places functions locally, Kubernetes default, which is the default scheduler of Kubernetes that places functions on nodes based on the node's performance. Random is another algorithm that is just random places functions. Performance metrics for us are operational availability, the duration of time a node has been available or up, function placements, the total number of replacements of functions, throughput, the number of executed tasks per time unit, response time, the average run trip of tasks. The first series of results are related to operational availability. We have 5 algorithms, and for each algorithm, we run the application, produce the task, and keep this going for 24 hours and measure the uptime or operational availability of 5 nodes. You can see 5 columns for each algorithm that shows the operational availability of 5 nodes. We are particularly interested in node 5, the green one, that was the least available node. You can see that the optimal and proposed algorithms could increase the availability of this node significantly compared to the default scheduler of Kubernetes by 33%. And also, when we look at the difference between the availability of nodes in a cluster, that is called like the balanced availability, we can see that the optimal and proposed solutions could minimize this more than the other ones. From another view, we can compare the longest available node and the shortest available node in the cluster, and you can see that the optimal and proposed solutions could minimize this one as well more than other ones, specifically the default scheduler of Kubernetes. Another series of results are for function replacement. Comparing the optimal and proposed solutions to the random algorithm that is another dynamic scheduler, we can see that it is significantly reduced. And this is mainly because of the policy in our algorithm that says only offload to a better zone and also stick with the node you are offloading. The local and default algorithms are giving the uh, 15 times placement. That means they just place functions once and they don't do any dynamic scheduling of functions. The next series of results is for throughput, where our algorithm could improve throughput by 15% compared to the default scheduler. And response time is when we are looking for trade-off, but you can see that our algorithms are giving very comparable results to the default scheduler. We have more experiments in the paper. And let's conclude. This paper investigated energy awareness at serverless edge computing, which means we mathematically model serverless edge computing environments and the scheduling problem. We devised energy-aware resource scheduling algorithms, and we implemented and prototyped serverless edge platform. We containerized IT applications and evaluated their proposal performance and achieved 33% energy efficiency while preserving the quality of service. For future work, we plan to go for heterogeneous resources like GPU and DPU. We are considering wireless and wired communications. Our application was IO intensive, So our application was particularly CPU intensive. We're going to consider I/O, memory, and data intensive applications. We're going to go for simulations to assist the scalability, and decentralization of the scheduler is a main task for us to do. Thank you.